First go to A, then go to C, then go back to A, and then we go to B, and then we go back to A from B, and then that would leave our result looking something like this. That's one possible solution. But the other solution would have been to go to B first and then go to C. What that would have looked like is A, B, A, C, A. Now, which one of these has a smaller lexical order? Which one of these comes first in sorted order? Well, the first character A is the same, but the second character could be B or C. Which one of these comes first? B comes first. So of course, of these two, we would prefer the second one. We would return the second order as our result. So that's something to keep in mind. And the way we can actually handle this is going to be pretty easy. I'll show you how we can, make sure that we return the smaller lexical order result. Now, this example is very simple because there's really only one, ordering that we could possibly create. And to get that ordering, what we could do is just run DFS starting at JFK. We know we're always going to start at JFK. We create a DFS running on this. And, using this DFS, technically, we are allowed to visit the same node multiple times, as I showed in the example just a moment ago. But what we can't do is go over the same edge multiple times. We can't reuse one of our tickets. But in this case, if we run a DFS starting at JFK, what we'll get is JFK first, then this one, then this one, then this one, and then this one. So there's really only one ordering, and you can see that that's the output for this example, the expected output. And so that's what we can return. But if we, of course, had multiple choices like this, or, adding a bunch more edges, and we still have to go over every single edge, and we have to return the smallest lexical order, let's see how we can do that algorithm. So like I mentioned, you really have to have a good understanding of graphs to be able to solve this problem. I'm going to assume you kind of already know DFS and the basics of graphs. So what we're
Ready to simplify your online learning? Us too. Go1 delivers the right training to upskill, retrain.
What we're going to use to do the traversal on this graph in the first place is, create an adjacency list. Of course, we're already given the list of edges, but we have to actually create an adjacency list out of that to be able to traverse over the graph. And the way we're going to be, creating this adjacency list is just going to be by using a hash map. We're going to map every single node to the, every single source rather, to the possible destinations that we can take. And the easiest way to build an adjacency list is just kind of iterate over the input, which is tickets in this case, right? It's a list of source destination pairs. So what we would do is say, okay, JFK has San Francisco SFO, at least I assume that's San Francisco. And then it also has a second one, Atlanta ATL, and we can start adding those to our adjacency list. Like this is the list, this is the source, right? So from JFK, we can travel to these two cities. But what I'm going to tell you right now is that we should have this list in sorted order because we're going to be running DFS. And as we run DFS, we're going to start at the first possible source that we could visit from JFK, right? We're going to try SFO, and maybe we find a result starting at SFO. In that case, we could return that as the result. But what if it turned out that maybe we could have also found a result, going to Atlanta first rather than SFO? In that case, this is the result that we would prefer because it comes first in sorted order. So what we want is for each of these lists to be in sorted order. And we could build the adjacency list and then sort each of these lists independently. But the easier way to do it is actually just to sort the input. And I'll show you why, because the way we're going to be sorting the input is by doing this. These are pairs of values, right? The first value is going to be the first key that we're going to use to sort. So, these two JFKs would be next to each other. But then if there's a tie between the first value, then we want to use the second value as our sorting keys. So among these two, which is going to come first, SFO or ATL? Of course, ATL because it comes first. That's just something to keep in mind. So if we have this in sorted order, then our adjacency list will be sorted by default, right? And I'm actually going to build this adjacency list now, assuming that this thing is in sorted order, or at least I'm going to be going through the sorted order version of this list of tickets. So first is going to be ATL, and it has JFK as one of its destinations. So let's do that. And ATL also has SFO as one of its destinations. So let's add that. Next, we have JFK. It has Atlanta as one of its destinations, and it also has SFO as one of its destinations. And then lastly, we have SFO, which only has one destination, which is ATL. So let's add that. So now we're going to start running our DFS. So let's focus on the picture now. So we're going to be starting at JFK. We have two outgoing edges from JFK. We could go to SFO or we could go to ATL. Which one are we going to decide? Well, we're going to look at our adjacency list and see which one comes first. Well, ATL comes first. So let's visit ATL. So we're going to go along this edge, and now we're going to be at ATL. And when we do that, we're actually going to remove ATL from our adjacency list, at least temporarily for now. And by the way, as we, go along this, we're also going to be building our result. Our result is just going to be, the travel history of these airports. We know initially we start at JFK, and right now we just visited ATL, so that's going to come next. Okay, now from ATL, we have two outgoing edges. We could go to SFO or we could go to JFK. Which one are we going to decide? Well, let's see which one comes first in sorted order. It's JFK. So let's go to JFK next. So we're going back to JFK. So we visited both of these two edges, and let's remove JFK as a destination from Atlanta. And in our result, now let's add JFK again, because we started at JFK, then we went to Atlanta, then we're back at JFK. Now from JFK, we only have one outgoing edge remaining, SFO, and that you can tell from our adjacency list as well. So let's pop SFO. Now we're at SFO. Let's add that to our result as well. Now from SFO, we only have one destination. It makes things easy for us. That's Atlanta. So let's pop Atlanta from here. Let's go along that edge and let's add ATL to our result. And from ATL now we only have a single edge outgoing. It's to SFO. So let's pop SFO, travel along that edge, and add SFO to our result. So this was a valid way because we just visited every single edge. How exactly do we know we visited every single edge though? Well, our result is going to be keeping track of all of the nodes that we visited in our graph, right? Not the edges. We know every time we visit one of the edges, we're going to be adding another node to our result. And we know that we actually initially start with a single node, which is JFK, before we even travel along any edges, right? We start at JFK. So basically, we know we are finished when the length of our result array is equal. So I'll write it out, is equal to the length of our tickets plus 1. So down here, you can see when length of result is equal to length of tickets plus 1, that's how we know that we are done. The plus 1 comes from the fact that we already start with a single node in our result array, and then every other node comes from traveling along one of the edges in our graph. So that's the main idea. Now, in this example, it was kind of simple for us because the first, solution ended up working. The first path that we tried ended up working. But if it didn't, suppose we actually had a graph that looked like this one, and let's say we started at the A node. In this case, we have two choices of where we could go. We could go to C first, or we could go to B first. We're going to choose B because it comes first in lexical order compared to C, so we travel along this edge and we end up visiting the B. Okay, well now we're stuck here. There's no outgoing edges from B. We can't even get back to A. So what we found is we tried to be greedy. We tried to take the first character that came, right, the alphabetical character, but it didn't work out for us. So we end up backtracking. We say, okay, we're actually not going to travel along this edge, at least just yet. We're actually going to travel to the C first, even though it comes after in order compared to the B, just because we know that at least here we might be able to create a valid path. So we go to C, then we go back to A, and then we go to B. So basically what we realized from this example is that sometimes in some of the cases, we're going to have to backtrack. So we might go along an edge and realize that it doesn't work, and then we're going to have to reverse our decision and then travel along a different edge. So that's something we're going to have to keep in mind. Let's actually jump into the code in a second. And stay tuned because it's actually going to be pretty tricky. But let's discuss the time complexity of this solution. And since I mentioned we are going to be doing some form of backtracking, the overall time complexity to run a DFS on the entire graph, in the worst case, it would be like V plus E, right? Basically the size of the graph. But since we are backtracking, potentially for every single edge that exists in the graph, the overall time complexity is going to be, the size of the graph squared. And, since we know that the number of edges is actually going to be, approximately the same or greater than the number of vertices, we can actually think of this as pretty much being E squared as the time complexity. And as the memory complexity, we can consider it to be big O of the number of edges. One, because we're going to be storing it in our adjacency list. And when we do the function recursively, this could be the size of the call stack in the worst case. So this is the time complexity. This is the memory complexity. Now let's code it up. Okay, so let's code it up. We are going to first create